Section 8-3 is on maxima and minima in plane and solid figures. The objective again for this section is given a plane or a solid figure, find the maximum or minimum perimeter area or volume. All right, so let's take a look at another example here from this section. Example 2, it says in the figure there, the part of a parabola, y equals 4 minus x squared, from x equals 0 to x equals 2 is rotated about the y-axis to form a surface. A cone is inscribed in the resulting paraboloid with its vertex at the origin and its base touching the parabola. At what radius and height does the maximum volume occur? And then what is the maximum volume? Justify your answer. Okay, so let's draw ourselves a sketch again. Start out these problems. That's what we want to do every time. So they said that it's the part of the parabola y equals 4 minus x squared from x equals 0 to 2. So that's just in the first quadrant, but it's rotated around the y-axis, so I'm going to sketch it like this. They're talking about this part of the parabola, and it crosses the x-axis at 2. It's going to cross the y-axis at 4, and of course when we take and rotate that around, we're going to end up with kind of this shape right here, this paraboloid. And then they say you inscribe a cone inside of this, and it's got the vertex at the origin for our cone, so we end up with a cone that looks like that. Okay, so the question that they gave us here is what is the maximum volume? At what radius and height does the maximum volume occur? So we want to maximize volume of the cone. Okay, so I guess the first thing we need to remember is what's the formula for the volume of a cone? Well, the volume of a cone is 1/3 times pi times the radius squared times the height. Now I want to put it in terms of this graph that I have here. Now this graph, remember, is the equation y equals 4 minus x squared. And in fact, I'm going to mark this point right here where the parabola and the cone share, and that would be the point xy, we'll call it. And so in my equation, volume is equal to 1/3 pi times the radius squared times the height. The radius of this thing is this distance right here. That's the radius, which that turns out to be the x value. So I can replace x, or the radius there, with x. So the volume is equal to 1/3 pi times, instead of the radius, I'm going to write that as x squared. And for my height, the height of this thing would be this distance right here. Is how we measure the height of a cone. That corresponds to the y value. So the y value is the height. All right, you can see I still have this in terms of two variables. It's still in terms of both x and y, but now it's at least in terms of the variables that I have in my equation. So I need to come up with a relationship between x and y. And the nice thing about these types of problems is they told you that relationship. It's right here. Y is equal to 4 minus x squared. So I can substitute that in for y. So I have volume is equal to 1/3 pi times x squared times 4 minus x squared. And again, I got to find the derivative of this thing, so it's probably going to be easiest if I multiply this through here. So I'll end up with volume is equal to, multiply the 1/3 pi x squared through there. So you'll have 4/3 pi x squared minus 1/3 pi x to the 4th. So there's our volume equation. And then for a domain for this thing, actually they told you the domain for this thing. They said that you're looking at the part of the parabola in the first quadrant there. So x was between 0 and 2. So x is going to go from 0 to 2. So there's our domain for this. All right, once we've got ourselves the domain, we can then find the derivative. So v prime is equal to, it's going to be 4/3 pi times 2x minus 1/3 pi times 4x cubed. And again, I want to find where that's 0 or undefined. All right, so let's do a little bit of factoring with this and see what we end up with. I have, I guess, a 4/3 pi I can definitely factor out. And I have at least one x in each of those two terms, so I can factor that out as well. So if I factor out 4/3 pi times x, I'll be left with a 2 in the first term. 4/3 pi is gone in the second term, and I'm left with an x squared. And that I want to find out where that's 0 or undefined. So I can clearly see from the first factor there, this guy right here, that when x is 0, I'll get a 0 out of this thing. And from the other one, the other factor here, if I set that equal to 0, you'd have 2 minus x squared is equal to 0. So that would mean that 2 is equal to x squared. So that means x is equal to plus or minus the square root of 2. All right. So we end up with the following values to consider here. First of all, x equals negative 2 is not even in the domain of my function. So I can basically eliminate the negative part of that. But I have x equals 0. Not only is that an endpoint for me, but it's also one of the critical points I just found. I have the positive square root of 2. And then the other endpoint was at 2 that we said. If we go back to our domain up here was for x's between 0 and 2, including the endpoints. So those are our critical points we need to consider. So let's take our volume equation and plug in those three values. I've got to find my volume at 0, my volume at the square root of 2, and the volume at 2. Now again, you can probably look at this, well, even if you go back to the graph of this, you can see why the endpoints aren't going to make any sense. If I make the x value, which is the radius, equal to 0, I'd have the tallest cone I could have, but I'd have no radius, so there'd be no volume. And if I make the radius as large as possible, make it equal to 2, you can see how I'd have the biggest radius, but I would have no height, so the volume would be 0 again. So I'm expecting to get zeros at the endpoints, which means I'm fully expecting that I'm going to have my solution right at the square root of 2. But let's just double check what our calculator gives us. And I'm going to put into y1 just our equation here for the volume. So we have 1/3 pi times, it was x squared times 4 minus x squared. Now you can put in any one of the formulas that we had written down for volume there. I'll put in this form just because it's easier to write that one. And let's just go to our table, and we will put it into ask mode and have it generate the values at 0, square root of 2, and at 2. And again, like I suspected, at 0 and 2 we got our zeros, so at the square root of 2 is where our answer is going to be. And it turns out we get 4.189, it looks like. 4.189. So these are zeros, and this is 4.189. And again, this is volume, and we're measuring here. They give us units for this one. I don't think they gave us any units to work with in this problem, so we don't have to worry about units, I guess. So we have volume is equal to 4.189. That's clearly our maximum volume. The other ones are 0, so this is our maximum volume. Make sure you clearly indicate that, by the way, in your answer. Don't just leave it written out with all those different values and not indicate which one you're claiming is the maximum. But go back and read the question. Make sure you've answered the question. It says, at what radius and height, which we haven't answered yet, does the maximum volume occur? And what is the maximum volume? So we've answered the second part of the question. What is the maximum volume? We still have to find the radius and height. So remember that the x value is the radius. So the radius, which is equal to x, turned out to be the square root of 2. And our height, again, if you go back to your sketch, you can probably help you see this, but your height was equal to the y value, and the y was equal to 4 minus x squared. So that would be 4 minus the square root of x, excuse me, square root of 2 squared. And 4 minus the square root of 2 squared, I guess I can write it out that way first. Square root of 2 squared is 2, so 4 minus 2 is 2. So our height would be 2. And so this is our radius and height of this cone. All right, that's the end of this section for us.